theory, different types of classifier, probabilistic, generative classifiers, discriminative classifiers, and discriminant function. And then I also we also discussed about the logistic regression. And so basic all hypothesis, cost function, and that is all is done. Logistic regression is used for binary classification because the hypothesis function, the sigmoid activation, sigmoid function that we are using, that is because of that it can be used only for binary classification. But we have a trick which is known as this one versus all or the one versus rest, which can help us to use the logistic regression for the multi-class classification. Okay, so now I had also asked you to go through these two problems which are there in the slides. Did you get time to go through? Did anyone get time to go through? So I'm not, silence means no, right? I thought you have exam in 2 weeks, so you people must be at least opening something to study. Okay. Anyway, so this is the NLP problem, where from a text will perform the sentiment analysis. Whatever example we have seen till now, especially machine learning, for the machine learning algorithms, what happens? We generally use the structured data. For that, it is more popular. When I say structured data, that means it is in the form of rows and columns, so which can be easily modeled into the metrics, and then we can apply any mathematical functions on those metrics. So that's the reason it's easy. Now, when we are talking about, say, text data like this, and we want to use machine learning algorithm, we have to do feature engineering. So we have to extract the feature from the text, and that's what it is done here for a sentiment analysis. As a domain expert, you have to find out what are the important features which will help me to solve my objective. Like here, objective is sentiment analysis, and these are the 6 features is is chosen. Now you do not ask me why the 6 features are chosen, because they are the randomly chosen. We are taking this a toy example. You may choose some, you may, depending upon your understanding, your logic, understanding of the linguistic, um, I mean the linguistic understanding of the language, you can decide any of the features. So here, say for example, the first feature which is chosen is count of positive lexicon. That means lexicon is, again, it's a term which is used in linguistic processing. It's a word, basically, positive word. So how many? There are 3 positive words. So you can see over here X1, nice, enjoyable, great. These are the 3 positive words. So likewise, there are the define features, and then as per that, whatever is a feature definition, we have got the some numbers for those features. So now you can imagine this will look like X1, X2, X3, X4, X5, X6. We have 6 features, and we have its values. 0 and this is 4.19. So this is one training example, one piece of a text for which we want to analyze its sentiment. So it's a fun training example, one row of your structured data. Then we can have such way, we can have another sets of text or lines, sentences, and similarly we can create another sets of features and so on. So what happens in case of text and images, we have to explicitly extract the features. So before the deep learning era came, this were the methods to be used, because machine learning algorithm, we have to do the feature extraction. So now it should be clear why we are taking this example. It is not in use currently. Nobody uses this method because we have so many advanced models and things become very simple. But to understand what is feature engineering and feature extraction, and machine learning algorithm requires the feature extraction, especially with the unstructured data. With structured data, we just do some kind of a processing or pre-processing. Yeah, and sometimes we construct the new features. So extraction is a term used basically for the unstructured data. Now, once we have created this way the rows, then it becomes a standard problem. It is like our standard data set. And then we can apply the logistic regression. So what is the hypothesis function for logistic regression? It is a sigmoid function. And in this example, what is shown? Say, let's say, for example, we have taken some uh, initial values of weights. Assume initial values of weights. For a logistic regression, we can initialize weight as 0. Then during the training,
Ma'am, a doubt here.
Let me complete, then I'll ask your doubt. I'll answer
Sure.
your doubt.
Sure.
So when what I was telling, yeah, we can initialize this with a 0, and then during the gradient descent training, we will get the optimal values of W. So assume we have got the optimal values of our parameters, and we have to use this for our inferencing purpose. So we have got certain sets of weights, certain sets of biases. Then we apply our hypothesis function, testing, inferencing, which is nothing but 1 upon 1 plus e raised to w into x plus b. Rather than that, it's simply written as a sigmoid notation, sigmoid symbol. These are our w's, these are x. Now you know this x has come from our previous slide. These are the values of feature. Plus bias is given. And now you can calculate this sigmoid calculator. You can use, this is a value. Hypothesis function for the sigmoid, for the logistic regression, tells us the probability of a positive class. So we can say this 70%, with a 70% probability, we can say that sentiment is positive. Because it is threshold is 0.5, it is above the threshold 0.7, so this will be classified as class 1. And 1 minus the class 1 will give 1 minus the probability of class 1 will give us probability for class 0. With 30% probability, we can say that sentiment is negative. So which is class 0. So this way, if some unstructured data is given, you can use it for the classification task. Yes, tell me now.
My question is, can you go back to the previous slide?
Here?
Yeah. So I understood that how we took the negative, the positive functions, but how did we assign these weights? Is what I'm unclear.
How do we? Sorry, what you said?
For example, x3 x1 is equal to 3, x6 is equal to 4.19, x2 is equal to 2. How did we assign these weights? How did we assign these values?
Did I explain this?
Not yet.
I didn't explain.
Okay, fine. Thank you.
I explained this, right? So it's mentioned count.
Yes.
So I also showed you this count. I explained this thing. I don't understand. Is it some lag from what I'm talking, or I think I explained this. So is it something that you are not able to, what I'm saying, it is lagging with respect to the screen?
No, ma'am, it's good.
Okay, fine. Thank you.
So similar way, you have to just read everything.
So in the sentiment analysis, ma'am,
Yeah.
the more is better or less is better? I mean, you told 0.7 is positive, so the more we get.
So this is the hype. No, it's not with respect to the application. It is how we are defining our hypothesis function. Okay, so positive of a probability of a positive class. Our target value is y, 1. So here you have to assume this is our supervised example where the positive class, that is a sentiment which is positive, where the y will be 1, and for the negative class, it's a negative sentiment. So it's a negative class. So generally when the data set is given, this kind of information will be available to you. What you will consider as a positive class. Here I have assumed positive sentiment is a positive class, which is y equal to 1. So we are getting this probability of a 1. That means it's a positive sentiment as 0.7. So that's 70% probability for a positive class.
Okay, got it. Thank you.
So generally this is no, but this is another example of a structured data where we have got two features and one target variable. So you can see this is given to us ground truth and some interpretation of what is class 1. So you can easily see job offered. Yes, then it is class 1. That is generally generally comes in a problem statement, or you are a problem designer, you are the algorithm designer, ML designer. You have to clarify this thing, that what is the positive class, what is the negative class. Mathematically, it can only give us a positive class probability and the negative class probability. What you will consider as a positive class, it's up to you as a designer. Okay, so now this is a structured example. And when you look at this, this is where this example, where it will be after one iteration of gradient descent. What will be the new values of the parameters? So this is a training problem, a training numerical, say after one iteration of. So like the same problem which you did in linear regression, the similar kind of problem where certain hyperparameters are given, like learning rate is given, and it's been given to us what are the initial weights and regularization constant. That means lambda equal to 0, no regularization. This is how we will write our W transpose X or theta transpose X. 0.5 CGPA. So you can see all of these three weights are 0.5, 0.5, 0.5. So CGPA and IQ coefficients are also 0.5. Then you can use this hypothesis function and calculate the hypothesis. So here it is given to you how we can calculate the hypothesis. Now, after the first iteration, so you know what are the gradient update equations. So it's a theta 0 equal to, this is our learning rate, theta. So new theta equal to old theta minus learning rate. And this is for all training examples. So it's 1 by n summation. Okay, this is e. Okay, let me write this as alpha learning rate, and this is n. I is equal to 1 to how many examples we have? And then we will do h of theta x minus, that means prediction minus actual multiplied by the corresponding weight value. This is not so difficult to remember this equation. So that's what is applied for each of the parameter. That's what we need to calculate. So we have theta 0, this is theta 1, this is theta 2. And then apply 0.3 is learning rate here. There are 6 examples, 1, 2, 3, 4, 5, 6 examples. And this is prediction minus actual. So you can, what you can do, you can just, for your practice, you can make an Excel sheet and then you can calculate for every example. First, what is a prediction y hat using this equation, where you will substitute individual values of CGPA and IQ. So make that in Excel sheet, write the equation in the Excel sheet. So you'll get y hat, and then you can sum all of the y hats together here, sum. I mean, you can, sorry, you have to sum all the differences. Y hat minus y. So, solve this end to end. That's why only the important steps are given over here. After this, these are the answers. Please verify these answers, whether they are matching or not. If there is any mismatch, let me know. Let us know. This is what you will do as first iteration of after gradient descent in when you write a code. So you can do it for multiple iterations. After this, say what this question says. You have to read the question in the exam very carefully. Inference and interpretation. Assume this is the equation which is given. Theta transpose x given like this. That means your W0 is given as 0.4, W1 is 0.3, and W2 is minus 0.45. Okay, this is given. So assume it's the same problem. After certain iteration of gradient descent, this is what you are getting. Yeah.
So I have a question on this.
1 minute, let me complete. I have not completed yet. So now we will do the predict. So what is asked? Predict the job offered for a candidate with this feature value. So this is X1, this is X2, like CGPA and IQ. So during the prediction, some unseen example is coming. This is the unseen example. We call it unseen example. That means it's ground truth. Its label is not available. And then calculate this hypothesis function with the sigmoid formula. We have been given this equation already. So it will be 1 upon 1 plus e raised to, this will become what? Minus 0.4 minus 0.3 CGPA and plus 0.45 IQ. And this answer should be 0.31, which is less than 0.5. So Y predicted will be 0, which is class no. That means, I mean, negative class. That means job offer is no. Yes, please.
Yeah. So, ma'am, can you please go to the previous slide?
Hmm.
So, from exam standpoint of view, ma'am, if we are getting such kind of questions, then the
Yeah.
3 columns, the table is already constructed with CGPA, IQ, and job offered.
Yes.
So, what we need to do is we need to create few more columns where we first calculate. We need to calculate the y hat with the given formula h
Hmm.
hypothesis theta x, and then we need to calculate the first we need to calculate the hypothesis theta x, and then we need to calculate the difference of these two, like y hat minus y. So such kind
Yes.
of table we need to construct in order to get the answer, is it?
See, table, so I'm telling you, it's easier for you how to solve it. It is up to you how do you do it. Okay. So if you write down, if every example you write down here, what is y hat, then you have to take y minus y hat, another column, and then symbol at the end you can end it. It's easier to do it. You can directly apply inline. You can also solve inline in this equations. That's up to you. Okay, why I'm telling you table, because you can do it with Excel and then you can do it with pen and paper. Another column y hat, another next column y minus y hat, and then at the end you have to simple do the sum. Up to you. That is only for this part. Okay.
Only for this part, and then we need to multiply by the
Sorry.
individual.
No. Sorry. One more column will come here. If I am just looking at this column, this multiplied by y minus y hat multiplied by their feature value xj, and then you take a sum.
Feature value.
Okay, summation
Okay.
is for this entire thing.
Okay. And
Now
then
you solve
feature value
inline,
of
you make a one minute. You solve inline, you make a table. It is up to you.
So ma'am, then we need to have the 2 more different column, right? One is multiply by CGPA and 3 more column.
3. Yes.
If it is
Or
for
you
only
solve
one,
it, or you just do
Mhm.
inline. Yeah, here only you can write down. You can expand the equation. It's up to you. Yeah. Yes.
like I was asking, if it is for only one iteration, that is fine. Will we get more than one iteration? Like for one
No,
iteration, why
no. Nothing like that. You will get no. Generally, when we create the problem, we create such a way that you have to do minimum calculation and maximum thinking. Okay, this is just an example because we know you won't get Excel sheet in the exam. Yeah, so it will be always minimum calculation and maximum thinking. One problem might come where you little more. Already previous year question paper is uploaded. You can have a look at it. So that's a general idea: minimum calculation, maximum thinking, and reasoning.
So ma'am, will we get enough time to solve at least one question paper, previous question paper in the class, like today or maybe in the next class?
We have a lot of syllabus remaining. We will solve. That's why it's given. You have to solve and come back. We won't get time that I won't get time to solve it. That question paper is given with the answer key. Very detailed answer key is given. So you have to solve it at home, and then we will have a doubt session in the class.
Okay, sure,
That is
ma'am.
only
Thank
way we
you.
can go ahead. Okay,
I mean,
so
the
I'll go.
previous example, that initial values and all those will be provided, or
Yeah. Question will be provided. So I suggest already question papers are uploaded. Just go through it once. Take your time, go through it once. So your lot of questions, lot of queries regarding the exam and the paper would be resolved. Okay.
Another thing, right, ma'am, in the formula it's x power of 5 and y power of 5, right? So, but why we are calculating y minus y top?
Sorry, what you are telling, you are not audible.
Sorry, in your formula, right? So it's a hypothesis of x power of I and minus y power of I, right? So, but in the column, we don't have that column. We have only one column y minus y to the power.
No, I still don't understand your question. It's the same thing what is mentioned in formula.
Okay. But in the formula, we are seeing that hypothesis of x power of I and y power of I, right? Okay. Okay. Yeah.
In the beginning, I said, please remember the notations. Y hat is just a shorthand notation of hypothesis function because this is little big to write. So every time I write this y hat, the same thing.
Okay. Okay. Thank you.
And you will find in every book, every literature where you will read y hat will be denoted for the prediction, and h of theta x is also for prediction. They are the different way of writing the same thing. Okay, now regarding the quality of the fit, the argument will remain same what we discussed in case of a linear regression. So anything, if you have forgotten, go back to that recording and please come back rather than afresh asking questions. So what I'm telling here with respect to logistic regression, what will change? Underfitting and overfitting concept. If we have a very simple model in terms, now it is in terms of a classification. As you can see, this data, the triangles and the cross, they are not linearly separable. Okay, so linearly separable data will look something like this. We can get very clear a linear line which distinguishes between one class and the other class. Now here that's not possible because both the class data points are into each other's region. And in that kind of a data set, when we try to fit a line, that means it's a very simple model. As you can see, it's a linear model, which will have our error will be high. So this will have high bias. Compared to if we can have this kind of a non-linear curve, which separates both the classes, our error would be reduced. So how we can get this kind of a curve? It's a quadratic curve. Some kind of a basis function, we can use it over here. Now you know what is a basis function? Linear basis function. The way we can use it for linear regression, it can be used for logistic regression also. Or the third case where this hard to classify example, I will call this as a hard to classify example. To cover it, to correctly classify this example, we are coming up with a very complex decision boundary. Okay, this is example of a very complex decision boundary. Then this is the case of overfitting. Why is this a case of overfitting? Because this example may be due to the noise. So rather than trying to correctly classify each of the examples, like the second case, we can leave certain example maybe misclassified, because this is what we are doing during the training. Even if certain examples are misclassified during the training, it is okay, because we are interested into good generalization performance. That is good performance when our model is subjected to unseen data, like during testing, during inferencing, during real-time development. So we are always interested into just fit data, even if we have a certain train error present in our during the model training. So that's the concept, same concept. In fact, this is the same concept applies to any machine learning algorithm, any deep learning algorithm. The idea of overfitting, underfitting, bias, variance will not change. Okay, so as we have discussed a lot of technique about regular, how do we handle overfitting? Underfitting can always be handled by going a different model, little complex model. So if we tried with this kind of a model and we have observed our training error is high, we can go ahead and try to implement the second model and we can get rid of underfitting. Overfitting is very difficult to identify and to get rid of. So regularization is one mathematical technique. Rest of the technique will also apply. You can have more training data, or you can reduce the dimensionality of your data set. All this will apply in general. They are not algorithmic specific. I'm only talking about regularization because here our cost function is different. So these are the equations. When we have, again, the regularization term will not change. Only what is changing in case of logistic regression, the cost function itself is changing. When we compare with the linear regression, which uses mean square error, here it uses cross entropy cost function. So what we do in the regularization in case of, say, L2 regularization, here, we add a regularization term in our cost function. So this is the idea here. The cost function is cross entropy. In that we are adding this regularization term, and you can see we are taking sum or square of all the parameters. It's a L2 norm. Same thing. Even linear regression also we add the same equation, same term we add at the end of the cost function. Lambda is as usual regularization constant, and this is about the training examples. How many training examples that we have. And similar way, we will observe changes in the gradient update rule. So this is a gradient update rule for the regularized logistic regression. And as usual, we will not regularize theta 0. These are the general theory which is applicable here as well. Okay. Yeah, there are certain self-learning thing. If you are interested in going into deeper mathematics, it's given here in your time. That's not important from the exam point of view, but for your understanding how certain derivations are coming. Okay, so here I'll complete logistic regression. Anything?
So, ma'am, here also the L1 regularization and
Yes, it will apply.
all the
Logistic net.
okay.
Yes, yes, it will apply. So that's what regularization theory applies to every algorithm. I mean, the similar kind of algorithm. It applies to decision tree also, but the way we do it, it's different because it doesn't use any mathematical function. Okay. So I'll start the next one. So again, my question, did you get time to go through this?
No, ma'am.
No, ma'am.
You have to get some time. Because what I understand from the last class, you all are finding only machine learning course more difficult. So at least give some more time to it. Okay,
Yes.
so what we are doing now, what we will discuss, a different classification evaluation metrics. So after what I explained, the first regression algorithm, linear regression, and then we discussed about a different regression evaluation metrics. So after now here, the first classification algorithm is covered, logistic regression. Then we'll cover different classification evaluation metrics. They are true for all kind of algorithms. They are not only for the logistic regression, but we are discussing over here with respect to logistic regression. The first thing is confusion matrix. It's simple, a 2 by 2 table. It gives us what happened versus what should have happened. So we'll create a table where this is the actual values which are given in our data set, and this is the predicted values. So what predicted by our ML system, and what you see over here, this is for binary classification, class yes, class no. The actual ground truth is yes, actual ground truth is no. What prediction is yes and prediction no. So this kind of table we will make, and then there are 4 numbers in the table ABCD. This will tell true positive, false positive, so as a name, it's a literal meaning, so you can understand what is true positive. Can somebody tell me?
Like
The expected result was
ground truth is also yes, and machine learning also says yes.
Correct. So likewise, you can understand what are the rest of the terms. Okay. So now the question, mistakes are what? Our false negatives and false positives are our mistakes. So question is, which mistakes are worse than other mistakes? All are mistakes. So that will, again, you need a little understanding of your domain. So first we will see there are a lot of evaluation metrics, popular, many evaluation metrics, but yeah, we will see some of the popular evaluation metrics. The first one, very simple, is accuracy. This is a formula for accuracy. And if you try to understand intuitively, number of correct predictions Out of total number of predictions. Someone is unmuted. Please mute your mic. So out of total prediction, how many are correct? So that will give us the accuracy. True positive, true negative. These two are the correct predictions. And in the bracket, in the denominator, we'll have all the 4 additions, total number of predictions. Okay. Now, what is the problem with the accuracy? Suppose we have this binary classification problem where class no, there are 990 examples which have got their label as no, 0. And there are only 10 examples which has got a label as yes. This is a problem, or I can say this is the so many times as a real world scenario where one class representation is more. You can say this is our data set. We have some features, then we have its ground truth, and I have say 1000 examples. In this 1000 examples, 990 example, up to 990 examples say they all are 0, 0, 0, and only 10 examples we have 1. We call this as a class imbalance. If we have a data set, such class imbalance, and if we calculate the accuracy, say for example, if a model predicts everything to be class no, so this is our confusion matrix. True positive is 0, false negative is 10, false positive is 0, and true negative is 990. And if you calculate the accuracy, this will come out to be 99%. Now, is this a good model? For example, you are talking about the intrusion detection. You are modeling intrusion detection system, fraud detection system, or a defect detection system, where the intrusions, frauds, and defects are your goal to identify, to predict. And in many such cases, intrusions are definitely very less. Network intrusion or any such intrusion, or the fraud, credit card fraud, or the loan default, all such cases are very less. So if you will encounter this kind of a data set where this is known as a minority class, and your objective is to identify, to predict the minority class correctly, and minority class is less in number. In that case, 99% accuracy. This is a model. Okay, after model, you are evaluating its performance. Now this evaluation we will do on trained data or test data?
Test data.
Test data, correct. So this is what you are getting it. Will you accept this model?
No.
Because your interest is in the minority class and it is giving minority class, all minority class it is wrongly classifying. So that's a problem with accuracy. Now few more examples before we go ahead to another measure. This is just, I've mentioned, it's mentioned here, kind of a case study. But what you need to look at these 2 tables. So we have a model 1 and model 2. Model 1 will have accuracy of 99%. Model 2 will have accuracy of 50%. You just concentrate there. Let me write true positive, false negative, false positive, and true negative. So which one is better? Can you tell?
50% one. 50%.
For which problem? Say the problem is car price prediction.
%.
99%. But the problem is, okay, fine. Even if it is an unbalanced, it's imbalanced data set, still car price. See, the cost of misclassifying your minority class depends upon your problem domain. Okay, so in this 2 model, if I have to predict the car price high or low, I have so many false alarm in the second case. Now, what is the importance of the minority class in a car price prediction, or what is important of a minority class for a cancer detection problem? If I have to compare this 2, so for car price, you are okay with the first model because it is giving me accuracy high. But if I go with the second model, maybe my minority class is correctly represented. It's correctly classified, but it is having so many false positives. So we don't want that for a car price prediction problem. But for a cancer detection problem, for a credit card fraud detection problem, wherever minority class is very, very important for us, that's our objective. I'll go ahead with the second problem. Ideally, both are not good, but if I just have to choose between these two, you have to find out what is your problem domain. Yeah.
I think madam this yeah, go ahead. Ma'am, I have a doubt in last, like how can we like how the class and type of like problem that is like we need to identify that here, because in first case we have 990 as a true negative basically, which itself says like this is not good. So why we are saying that it depends upon type of problem?
Anyway, it is not good. See, true negative. 990. So 990 examples are correctly classified as a negative class. Out of 1000 predictions, 990 predictions are correctly classified. True negative means the negative class is correctly classified.
Okay.
Right?
Okay, but how it is like how it will depend upon the type of problem? Can you please explain that once again? Like you were saying that for the class type like this, you can go with 99% like at times, and 50% at times is also can also be correct. Like that point I haven't got.
Okay.
It's just comparative analysis, right? It's not that this one is the best and that one is the
No,
worst,
no.
right? It's just
No,
a
I said
comparative.
you have got only these two models.
I think
In
it
that we
depends
are
on the
comparison.
question, right? So if you are asking about the class 2, with respect to class 2, if the prediction is good, I think
Yes, I said with respect to this two model.
Yeah,
And
yeah.
why it is in your problem domain? Same example here I explain about the cancer detection or the fraud detection, where my objective of my problem domain is to identify, say, cancer prediction, all cancer cases correctly. So in that case, I'm interested into the minority class. And here my positive class are the minority class. The number of class, yes, example. It's a positive class. That fraud is yes, intrusion is yes, defect is yes, or a cancer is yes, or a COVID is yes. But my goal is to detect that. And if that is not correctly identified, I will not be interested in that model. So the 991 is giving correctly. So what do you mean by 990 for true negative? It is correctly classifying the negative class. But my focus, my goal is to correctly classify positive class. Is this model doing that thing?
Okay, okay. No.
It is not doing that thing.
Yes.
Now, the second model is doing that thing.
Yes.
It is doing that thing. So in that case, I have to just compromise between, I find out between these two model, it will pick up the second model. But my problem is car price prediction, high and low, where I do not have any affinity towards any class. I want false positive or false negative combinedly should be reduced. In that case, I can go with the positive, the first model, because I got 990 which are true negative. That means out of 1000 prediction, my 990 predictions are correct. I may go with that.
Got
Okay,
it,
so
ma'am.
that's
Thank
the
you.
comparison.
Yeah, got it. Thank you for explaining.
Now, so this was the problem with the accuracy. So we go ahead with the another. There are another measures, precision and recall. This is a formula for precision. This is a formula for recall. Precision is number of positive correct divided by actual labeled positive. And here number of positive correct divided by number of actual positive. So these are the two formula, and I have written certain theory about it. I'll give you the example. You will be able to understand theory more better. Okay, before that, we are interested into high precision and high recall model. So this values would be between 0 and 1, and any value high precision of 1, recall of 1 will be very happy if we get from our model. So high precision, it's a name suggests precision. For example, you are developing a system for the safer video recommender system for the kids. So what do you want in that case? Whichever videos are recommended for the kids, they all should be safe. Even if some of the unsafe, even if some of the safe videos are not getting recommended. because you do not want unsafe videos to be, recommended to the kids. If that is your objective, you should look at the precision. Book recommender system. You know this, if I try to recommend 100 books, in that some of the books, like say 40-50 books, my client is actually liking it, but another 50 books, they are false positives. My client will not like it, and you are developing an e-commerce system, you will lose a client. So you want in a book recommender system to recommend only few books, but you should be very sure that your client will like those books. So that is, you are looking at the very, please mute yourself. You will want to be very sure your model should have high precision. So that's what is a precision. So we call it what proportion of a positive identification was actually correct. If I say 1, so when in this formula, when the 1 will come, when your false positive is 0. So here I'm interested to reduce the false positive as much as possible. Compared to the recall. So here, suppose a robber is robbing the shop and it has got a very limited time. So he will not go and check the value of every item. He will try to gather as much as possible, and then later on he can discard the not so valuable items. So that is example where we want to I can say we want to collect as much items as possible, even if certain items which are not valuable. So in this terms, I can say that system with a high recall might give you a lot of bad items. So what are the bad items in our machine learning term? Lot of false negatives or lot of false positives will come. Sorry, in this case, lot of false negatives will come. So when I say recall is low or recall is high, that means false negative will be 0. Bad items are false negatives. Okay, let's take an analogy with our shoplifting problem. False negative means the items which are not valuable. Those are the negative items, and the items which are valuable are the positive items. So all those items that we are picking up, everything will be picked up. So in that case, I'll be interested into high recall. So this is the difference between a recall and a precision. What proportion of actual positives were identified correctly? It is very difficult to achieve both high. Once we try to achieve precision high, the recall can be reduced. If we try to achieve recall high, precision can be reduced. So there is something called okay, F1 measure. One minute. Let me still this recall is remaining. Okay. Sensitivity is a recall. Again, I'll explain what is a recall, and then I'll explain specificity. The ability of a test to correctly identify patients with a disease. So high sensitivity catches all sick people. If someone has a disease, will the test find it? If that is what your objective, you will look at the high recall. Your objective is to catch all the sick people, even if some of the not sick people will be tested positive. That's okay, but you don't want to leave any of the sick people. Or the other way is something called a specificity is this, where we are going to reduce the, if this to be 1, false positive would be 0. And we are looking at the true negative rate. If someone doesn't have a disease, will the test correctly say they are healthy? So here our objective is to reduce the false alarms. We don't want to flag anyone not having a disease but having a disease. If that is what is objective, then you will look at the model with the high specificity. Yeah. Tell me.
All good, ma'am.
I have few more
In
examples.
robber,
Huh.
yeah, in robber example, what is the specificity? Like, able to identify less valuable items.
See, robber, you won't be interested in specificity, right? You are a robber, you want to gather as much valuable item as much. So you will do that, even if some of the non-valuable items are coming up. That's fine, right? It's like valuable item is catching, valuable items catching sick people. Try to relate that way. So you will be interested in high sensitivity. So you can't achieve all of them. So you have to make a decision what you should look in your model. Now there is a F1 score specifically used for a class imbalance cases. That formula will look at where we have both recall and precision, both are high. So you can look at the formula. This is a formula. There's a formula in terms of precision and recall. So it's the F1 formula. Now let's look at the example. Again, we have these two models, and these are true positive cases, false positive, false negative, true negative. First model, based on a formula, we have calculated precision. For the first model is 0.5, recall is 1, F major is 0.62, accuracy is 0.99. And then we have something in the second model. True positive, false negative, false positive, and true negative. Now you don't know the domain, but just by looking at these numbers, both of the model, our accuracy is high. Okay. One model is having recall high, another model is having precision high. The first model having precision moderately high, but the second model is having recall very low. So in this case, how to choose it? So F measure will give you a correct way of choosing it. Look at the high F measure. So this is 0.62 and this is just 0.18. So without having the domain knowledge, you can choose this model, first model. Again, the question is you have to choose between these two models only. So the F measured high. So this way F measure is a very reliable metric which will make you to make a decision. Now look at this. Suppose this is the problem of cancer prediction. And one is to look at the F measure. The other way is you want to look at the recall or a precision. You want to understand what is interpretability for the recall and precision. Suppose you want to make sure all people with cancer will be caught. And you don't want to leave any person having cancer. So in that case, there is a possibility that people might not be having cancer. They will also be flagged as having a cancer, but that's okay. So in that case, you will look at the recall, high recall, where you want to reduce the false negatives. Person having a cancer, but your system is flagging it as a not cancer. So that's your objective. Same cancer prediction problem. If your objective, say that confidently a person has a cancer. So in that case, you want to look at the precision. So suppose when you are modeling this problem, cancer prediction, there are multiple tests that you will do. The first test, you will gather a list of all the people. You will try to maximize the recall. Person having cancer, not having cancer, everybody will come. In the second test, you want to again get some more data or change the model and then look at only for those people who have been flagged as having cancer. And you want to say confidently as a person is having a cancer. Maybe we are doing some extra test, we are getting some extra results like biopsy and all. And then this is a time that you want to make sure that a person is having the cancer. So in that case, you will be looking at the precision. So same cancer prediction problem, you have to define what is your objective. Depending upon that, you can decide which is important for you, recall or precision. Again, say simple example, not so trivial, not so life-threatening medical problem, spam email prediction. So all numbers are same. If you do not have a domain knowledge, you can pick up this F measure 0.62 and you can pick up that model. But again, now you are a domain expert, so you want to find out. You have to ask the questions. you want to make sure all spam emails are filtered. That is your objective. You don't want any spam, even if certain non-spam emails are getting filtered and going to a trash. But you want to make sure all spams are not coming in my inbox. If that is your objective, you will look at the high recall system because you want to reduce the false negatives. They are the spam, but your system is flagging them as a not spam. Compared to now, you change your objective. You want to confidently say that email is spam. Your confidence level you want to increase. You don't want non-spam emails to be flagged as spam. In that case, you want to reduce the false positive and you will use a system with high precision. So without a domain, so what is the takeaway? Without a domain knowledge, you can look at the F measure and pick up the higher F measure. With a domain knowledge, with clarifying what is your business objective, then you can decide on whether to look at the high precision model or high recall model. Okay, clear this. So I'll go ahead with regarding again some more importance about the F measure.
Ma'am, just a small
Yeah.
query from my side.
Uh.
Like you were saying, like in first cycle we will get certain level of precision, and again we can go back and perform the second cycle. So in second cycle, like we can completely change the model, or like it will be just an iteration of the first cycle. Like,
see the model 1. This is model 1. See, cycle is, I said this is model 2. Okay, what is defined? What is a model? One is you can change the algorithms, or you
yes,
can change the hyperparameters. Okay, or you can change the data. So all of this, if you're changing,
okay,
that means you're coming up with a second model, another model.
okay, got it.
Like in case of cancer prediction, you can get the additional data, additional test results. Some additional tests have to be done, right? This is how we the healthcare professional do. Some basic test, then another test, then another test, like that. You can keep on increasing your data.
Yes, thank you.
Okay, now with respect to skew, low skew. That means it is balanced. I can say this is the balanced data set, almost balanced. That's why it's a low skew. Okay, so you can see the class, actual class, yes, I have 100 example. Actual class, no, I have 100 examples. In the second model also, this is actual class, yes. Again, I have 100 example, actual class, no, I have 100 examples. So they all are balanced. Again, here also 100. So this is a thing with the balanced class set, very low skew. In this example, I have equal representation for the yes class and equal representation for the no class. You can say, you can add this too, you will get it. And then we calculate all of these measures. And when we compare, you will look at the other measures. See, precision is 0.98, precision is 0.9, hardly any difference. Precision is 0.99, hardly any difference. Okay. So again, F1 measure will give us a correct indication. So you can pick up the model with highest F1 measure, which is 0.99. And now we will look at the precision, which is having high precision and high recall. So that's a good model. Now I have a medium skew case, a medium class imbalance. Yes class example 100, no class example are 1000. In each of the three models, so for this imbalanced data set, we have trained these three models. 100 and this is 1000. Again, if I look at the F1 score, we can pick up the F1 score, highest F1 score model. And if you look at precision is high, recall is also high. So F1 is good measure. What I'm trying to prove is it is a good measure for class balanced or class imbalanced cases. Or the third case where we have a high skew, very high skew. This is 100 and this is what is 10,000 examples. So I can say this is a very high class imbalance. Plus class, positive class only 100 examples, negative class only 10,000 examples. And again, maybe our F1 score is very low. So anyway, you have to come up with some better alternative. But even if you have to choose between this 3 model, you can still rely on F1 score, which is having the highest value. You can then compare their precision and recall. You will find there is a trade-off between precision and recall. They are good for this. So that's the reason when you have a class imbalance, F1 score is a good measure to choose the model. So these all are techniques of the model selection. Okay,
Ma'am,
so I'm done.
one quick
Yeah.
question.
Yeah.
These TPRs and FPRs we can calculate by seeing this data, like basically.
Yes, they are formula. It's mentioned. All of these
Yes,
are
correct.
formulas. Yeah, you can calculate from your data. Simple, you have been given data, test data, okay, and their ground truth is anyway given. Your prediction is given. Find out how many are correctly classified and how many are wrongly classified. So you will get all this number from your data. You will have to populate this metrics first from your test data. I mean, test data and prediction on the test data.
One quick question, ma'am. Last. When we should say that it is good to select F1 when means in terms of skew perspective. So when we can say that it is highly skew and when we can say that it's medium skew. I know that any percentage between that. So 10%
No,
of
no,
data
no.
will.
That will be you can see your data set, right? You will do
Yeah.
some data set summary statistics of your data set. So that you will be able to see, no, this is 110,000. So it's high skew. See the ratio. Now ratio is up to your business domain. You have to which ratio is high you consider as imbalance. But you can see compared to, that's why the 3 examples are taken. No, that's a low, I mean medium skew.
Okay,
This is
10% of
100 versus 1000. There's no thumb rule, so I cannot say in terms of percentage.
Okay.
Okay, there is no way. These are not a fixed thing.
Yeah, sure.
This figure will come like based on the business discussion, like when we are like discussing with business, like then we can decide on this, like skewness. Is this understanding correct?
Yes. In general, you can say when I have to compare between this two, definitely I'll call this as a high skew case. Right. So, but if I have to compare 100 versus say 120, then definitely this is a high skew case. So all are very subjective.
Thank you, ma'am.
Is it necessarily true that with high skew the F1 score is gonna go low?
Yes, this is showing over here. The evidence is showing here in this 3 comparison. See, you compare 0.94, 0.01. Sorry, 0.099. The evidence here is showing like that. So it says you have a very high class imbalance problem. So you will have a problem in a lot of majors. Won't be so clear. But then see again a problem. You can see the recall is high. So even if F1 score is low, you see what is your objective. Should I take, like, I should catch all the sick people correctly, even if I'm catching some of the non-sick people. I'm flagging some of the non-sick people as sick. If that is your objective, this is good to go, even if F1 score is not acceptable, because the recall is high. Okay.
Yeah.
And precision is also not bad.
I think, but yeah, I mean there are too many parameters because F1 is gonna depend on the precision and all the other variables that are playing a role in F1 calculation, right? And on top of that, the skew data is making an impact.
So here more of interpretability will come into it. You have to make a decision and you have to communicate that decision to your managers, which one is better, why it is better. So some of the points we have covered here. We cannot go, there is an entire course on fact in your, I think, second, third semester somewhere as elective, which talks all this fair, accountable, transparent machine learning, where you are making certain decision. You are going to reason about that decision, why. So a lot of things will go in detail. So some of the interpretability part I have also uploaded, that those with respect to linear regression. Some of the interpretability we may cover, like here we have covered. Okay, you have to communicate this decision. So what will you communicate? Why did I choose this model? But there's a lot more theory into this interpretable machine learning. Okay, the next one is another measure called receiver operating system, receiver operating characteristics. it is a curve against TPR against FPR, true positive rate and the false positive rate. So what is that? Fraction of positive examples predicted correctly. So it is nothing but a sensitivity. That means it is nothing but a recall. So on the y-axis we have a recall. On x-axis we have a FPR, which is 1 minus false specificity. Oh, sorry. It's 1 minus specificity. Fraction of negative examples predicted as a positive class. Okay. Now, again, there are the formula for TPR. This is a formula. So you all have to sit and just write down all the formula and compare all of them together and try to intuitively understand what it is trying to tell. So this is a curve. So we'll take false positive rate and true positive rate. This is TPR curve and this is FPR on the y-axis. And say this is a model 1 and this is the blue line is a random guessing. Without any machine learning, you're randomly predicting the output, randomly predicting the class of your data set. So that is always, we say 50% times you are correct. When you do a random guessing, 50% time your guess is wrong. So based on that, when we then calculate FPR and TPR, you will get this blue curve. Use the Excel sheet, take some dummy example, draw TPR and FPR. This is what you will get. Now our model should at least perform better than random guessing. If it performs worse than random guessing, then what is the point of doing machine learning? Because randomly you are picking up with a probability 50%. Some of the example will be classified as 1. Some of the example will be classified as 0 randomly. So that's the ROC curve will tell us whether your model is performing better than random guessing or not, which is 50%. So when we draw this curve, we have got a certain coordinates. So this is a 0, 0 coordinate. Then this is 1 and 0 coordinate we are interested into, and this is what 1 and 1 coordinate. What is the interpretation of when? Your false positive rate is 0 and your true positive rate is 0. So what do you mean by 0, 0? TPR, FPR is 0, 0. Model predicts every instance to be a negative class. So when you are here, false positive is 0. And true positive is also 0. That means there are no positive examples. There are no positive labels. Everything will be predicted as a negative class because FPR, TPR, it's a positive rate, false and true. Everything is 0. So cancer test with respect to our cancer test says no cancer for everyone. Will you be interested in this kind of a model where TPR and FPR would be 0? No. Compared to, I have say 1, 1 here, where the FPR is also 1, this coordinate. So both X and Y axes are 1 at this point. TPR, FPR, both are 1. So when you are this coordinate, model predicts everything to be a positive class. Your true positive rate is also high. Your false positive rate is also high. That means everything is predicted as positive class. Cancer test says cancer for everyone. You also don't want that situation. So what do we want? This is the ideal. So true positive rate should be high and false positive rate should be 0 here. So this is a coordinate that we are interested into. So what is its interpretation? It catches all the cancer patients and never flags healthy people as a cancer. So you can see as we are, our true positive rate is increasing. Our false positive rate is also increasing for this red model. So this is an interpretation of ROC curve. Now there's something called area under the curve. So area under the curve is, you can integrate area under any region is integration. So we get a score, AUC score. This curve is with respect to your, there's no score coming over here. You can draw the curve and then you have to interpret how this model is performing. compared to when we have this score. So this will give us a number. So perfect number is 1. It is nothing but area under the curve. So when will you get a perfect one? Where your model and your graph is here, something like this. So area, if this is where your model is, so area under the curve will be the entire canvas. That means your score will be 1. Similarly, below this dash line, that is our 50%, random guessing. AUC score will be 0.5. So any score between 0.5 and 1, like our green model, it is above the dashed line with some AUC score is acceptable model. How much you want to increase, that's up to you. So that's what is AUC score. And from our sklearn metrics, all of these metrics are readily available. You don't have to write any code. You can import ROC AUC score and you can print it once you perform, and then you can use this score to identify. So we always choose for a model, like I have ROC1 model here, I have another model here, I have another model over here. I can choose a model whose this AUC score is high. Yeah, see here it is mentioned there is a comparison of two models, M1 and M2. But again, if you see, you won't get, you can check the AUC score, whichever is high can be picked up. But if I want to interpret this to model, the dash line is my random guessing. Both the model is showing the performance, which is above the dash line. But you can see for this is a crossover point. For lower false positive rate, the model M1 is correct. For the higher false positive rate, the model M2 is correct. So this is what is interpretation of ROC curve, which we will get the trade-off between false positive and true positive rate. Now the question comes, how these points are coming, false positive rate and true positive rate. So we have got one model which will give you the one positive rate with one threshold. Then for that model, you can change the threshold. You will get another data point. Then you will again change the threshold. You will get another data point. So this is how we can draw this curve. For a same model, if you change the threshold, like for logistic regression, we're using 0.5. But suppose if I want to check for a different threshold, what is the effect? So likewise, for a classification algorithm, we can change the threshold and we can check this FPR and TPR. So that's one example, which is how we can draw the ROC curve here shown. So say, for example, use those classification algorithm, which will give us the continuous valued score. So probability, you can think about naive Bayes is a algorithm which can give us in terms of probability and where we do not have a fixed threshold. Logistic regression also gives us a probability, but we have a threshold of 0.5. So that's a general threshold is chosen, but you want to see the effect of changing the threshold. So say you can use any classifier which can give us this continuous valued score. Say this is a classifier and this for 10 different examples, test example. This is a score which we are getting, AUC score. And we know it's true class because it's a test data. The ground truth is available with us. So some of them are positive, some of them are negative, and so on. Now we will create this table where all of this. So what we are taking this score. Oh, sorry, this is not AUC score. My bad. This is, I can say this could be a probability score. So for the algorithm which are giving us output in the form of a probabilities, these are the probability for every example. So we are just simply arranging this in the ascending order first. Start from the lowest probability to the highest probability. For our training instance, we have got a probability for each, sorry, test instance, we have got a probability for each of our test examples. And then we have the actual class with them. These are the actual class. Now consider this, each of this as our threshold. And then we have created rest of the rows where we are calculating true positive, false positive, true negative, false negative. Once we have got this confusion matrix, we can calculate any formula. We can use the, here we are calculating TPR and FPR because I want to draw this ROC curve. For that, I need just TPR and FPR. So how it is done? First, say for example, first we are taking threshold as 0.25. So it says that greater than or equal to threshold if the prediction is greater than or equal to threshold, or I can say the score, then output is a positive class. Less than threshold, score is a less than threshold, then output is a negative class. That's a prediction. Suppose if I take 0.25 as our as my threshold, what will be prediction? Just concentrate on 0.25. It's my threshold. So my score is greater than or equal to 0.25. You can see all of these examples are greater than 0.25. Yes. All of these are greater than 2.5, right?
Yes, ma'am.
Yes,
So
ma'am.
including it's greater than or equal to. So that means all of this will be classified as positive for the first threshold. Okay, let me write down over here. For the first threshold, all will be predicted or classified as positive class here. I'm just writing here for the first threshold. And these are the actual one, these are the predicted one. Now you can easily calculate how many are true positive. This is true positive, 3, 4, and 5. So 5 predictions are true positive. So we got TPS 5, and 4 predictions are false positives because they have been classified as positive based on my threshold, which is 0.25, but their actual labels are negative. So they all are false positive. Once we got this, we get a true negative and false negative also. And then apply, find out TPR, FPR. This is what we have got 1 and 1. First data point I got for to draw the graph. Then second. Okay, now suppose let's take 0.43 as a threshold. So anything my score greater than or equal to 0.43, my y hat will be positive class, and score less than 0.43, y hat will be negative class. So now I'm moving ahead. Take this as the threshold. So in that case, this will be, or if I write down here again, let me just take one more slide. Okay, I'm just showing here second where my score is greater than or equal to threshold of say 0.43. That's my next data point. Then the class will be positive one. So all of this will be classified as positive, and this will be classified as negative. These are my predictions. These are my actuals. Compare it and find out how many are TP and how many are FP for the second case, second column. So here, let's, this is correct, positive. This is correct, positive. This is correct. This is correct. So I have got 4 true positives, then false positives. 1, 2, 3, and 4. So there are 4 false positives. Then what about true negative?
No.
Sorry, this is wrong here. I was looking at, you should not look here. Here. Yeah, true positive are 4, and the false positives are 5. Yeah, we have to consider 0.43. I showed for the 0.53, but we were talking about 0.43. So I have got false positives are 5. And true negatives are 0, and false negative. This one
1.
is a false negative, 1. So we got this 4 number, apply the FPR, TPR, you got this number formula. So likewise, you have to fill up this table and get the value of FPR, TPR, and then start plotting. So this both are 0, 0. This 2 is here. Both are 1, 1. It's here. So red curve is what? This model's performance, ROC curve performance. And you can see for the lower thresholds, TPR, FPR both are 1. So for the lower threshold, everything is classified as positive. You can clearly see for 0.25, it's a lower threshold. Everything is classified as positive, which is also the same thing you can see from your numbers. The same thing you can see from the graph. So you verify your interpretation is correct. When both are 1, 1, like in this case, TPR, FPR both are 1, 1. That means everything, all instances are classified as positive. You can verify here that FPR, TPR 1, 1 is coming for a 0.25, which is a lower threshold. In this case, lowest threshold. And you can see everything is classified as positive. So it's verification done. This is a pen and paper method of drawing the ROC curve. Okay, anything else? There are certain examples for your practice. So try all this practice.
Ma'am, this threshold value, how can we identify like?
No. Yeah. So here how it is done, we have taken that probability. So we are doing this on a test data. You have used the logistic regression or naive-Bayes algorithm or the neural network algorithm. You will get output always in terms of the, or I can say my output score. You will get in terms of this probability, and take each of this probability as a threshold. Generally, we say that for logistic regression, we take a probability 0.5. If your score is greater than 0.5, it will be classified as positive one. But ROC curve will also help you to select the models where we don't fix our threshold. So you can choose a model, which one is a good probability, which one you should choose. So you can see this value of FPR, TPR, okay, which is 0.6 and 0.6. After this, the model's performance is increasing, decreasing, whatever, but it is still below the random guess line. So which is up to this point, probably any threshold is okay, where both TPR, FPR both are 0.6, 0.6, say this point. What is its corresponding threshold, which is 0.85? So if you're lowering a threshold below 0.85, then your graph is going in this region below the blue line. Then you should not choose any threshold which is less than 0.85 for that model. So basically it's a model selection technique and the threshold selection technique. Threshold is one of the way you can create different models. You can do this also for a different algorithm. But yeah, we will learn ROC curve when you have to change the threshold. You have to identify which is the correct threshold. Then you can use this ROC curve. You're changing a threshold, your model will change. Model 1, one threshold, model 2, another threshold, and so on. Okay. So these are the, please, some problems are there given here. Solve it and just find out the answers. So you will get some practice on this. And refer the references which I generally write. Those are the books where this contents are given good. I'll start the next now decision tree. You want a 5 minutes break?
Okay, ma'am. Ma'am,
Yeah.
last question. So,
Yeah.
so our syllabus is still decision tree, or is it far more than
Decision
that?
tree. Decision tree.
Okay.
That's all. Decision tree. It's already published, right? It's already given your syllabus.
Ma'am, I have a question. Ma'am, we will take means one more day, like next lecture, to complete decision tree. After
Yes.
some time, ma'am, we will get time to revise also. Ma'am, you will help us revise by looking the papers and all.
So that's what I said. You come and solve the paper, then we can do doubt solving. When the area required, we will have to go. If decision tree won't be over, either we can spend some extra time next class, or you have to come up with the extra class. So let me start first. We'll discuss. Okay.
Okay.
Let's
Okay.
not waste our time in discussing this. Manoj, leave job, just study. I don't know. I can't comment on that. Sorry. Yeah. Please, I will take a break and then I'll start decision tree.
Yeah, sure, ma'am.
Ma'am, I have few questions from the previous slide deck that we completed it. If it is possible at the end, we can discuss, or now also if it is possible.
Hello, ma'am.
Yes. Yes.
Yeah, I just wanted to understand, can we get a consolidated all the recordings for all the sessions somewhere?
It's there on Teams.
Okay, but one recording, it is there. Like, if you want the entire all for the first semester, whatever are the recordings,
I
entirely
don't think so.
one
No, no,
place
no.
somewhere.
No, I don't think so. You just have to click individual recording. No, what's so difficult in that? I don't know. You can't do that because I think Teams only, this is automatic recording generated. Teams, Microsoft Team is giving us that facility and it's going there. So beyond that, nobody would do that consolidation, that integration for you. And it just you have to click a different recording. You open 5 recordings, 7 recording or 8 recordings in your browser and just navigate through yourself.
Okay.
We can't have like one recording. That's not possible. You need to download individual session recording. Yeah.
Download also, I don't know whether can you download it?
Download कर सकते हैं, ma'am. Yeah, I have done that.
Oh, okay.
It's allowed. Yeah.
Let me know when can I start.
We can start, ma'am. I think all are back.
Okay, decision tree, it's not that difficult algorithm. It's more of a very intuitive if then else kind of a structure. So generally I have seen it is understood by the students very fast. If you have done so much of maths before and if you've understood all the theory, then this is easy. So it's a tree based structure. You all might have studied data structures long back. Even if you have not, it's okay. Nothing related to data structure will come here, but it's a tree structure where we have something called a root node, which is the top of the tree. Then we have a certain internal nodes. You can see the pink nodes. They are the decision nodes. And then you can see these green ones. They are the terminal nodes. So in terms of tree, we call it leaf nodes. Then decision nodes are the internal nodes. And then we have the root node. So it's a kind of a flow chart kind of a structure. Then by looking at like a tree, we have a branches. So from every root, we have the branches. Every node, we have the branches. See, this is one branch. We are coming out at this branch, and whichever are the nodes and the branches, we can call this as a subtree. There's an entire tree, then we have a different subtrees. So likewise, this is another subtree. Okay, so this is the understanding of a tree structure. Decision tree, internal node denotes a test on an attribute. Okay, this is important. Test on an attribute. Attribute is nothing but feature. Branch represents an outcome of a test. So see, this is the decision node. That means we'll make a certain decision, like if something is greater than 5, if gender is male, like those kind of if questions will come on this decision node. And the branches are the outcome of the decision. If a gender is male, then go left. If a gender is female, go right. And finally, our leaf nodes, they will represent the class labels, the final class labels. So how do we a very high level understanding? First, we have to construct a decision tree from your training data set. So at the start, all training examples are at the root. So we'll start recursively from the root. This is the recursive algorithm. What we will do, every node, the same process will be repeated. So we start with the root node, and then the tree is grown downwards. So in the beginning, everything will be, all our examples will be at the root node. Then iteratively, we will partition our training examples recursively based on the selected attributes. Just a theory, even if you do not understand, it's okay. We'll do one example, it will be really clear. And tree pruning. Okay, tree pruning, I'll talk later. See, this is example, mammal classification problem, where I have all of these features. Some characteristics of the mammals. And our class label, we have mammal, reptile, fish, amphibian, maybe bird. So it's a multi-class classification problem. So say I take in the root node, so body temperature is one of my attribute feature. So say at the root node, we have taken body temperature. You can take other node also. The node selection, the feature selection at each node, we will see. There is a theory behind it. Right now, I'm only explaining the interpretability of a decision tree so that you can understand how to interpret, what to understand a decision tree. Then we will discuss about how to draw the decision tree. So say let's example, this is my decision tree. I have a body temperature at the root node, and body temperature has got two values. If I go back at body temperature, warm and cold. Okay, so it's a binary attribute. It has got just two values. So only two values, you will have only two branches. Warm, if a body temperature is warm.
Madam, one question here, sorry. Does that mean it has to be, if it is a root node, it has to be binary?
See, this is a problem. You people don't let me complete anything. I've just started the discussion. I'll talk about multi-way also. That's there in future slides. Just have patience. Let me complete something. As I said, I'll come back to the questions. When there is a natural, I know what is coming in the future. You don't know that. I'll answer your answer. I'll answer your question in few slides. So say this example, in this data set, my body temperature has got only two values. It has got two values. That's why it has got two branches, warm and cold. So understand, when I go to body temperature towards the warm side, then I have another feature, which is gives birth. Where is that gives birth here? Here. Gives birth, X4. And you can see I have two values. Again, For a gives birth, I have only binary values. It's a binary attribute. So in the gives birth also I have, because it's a binary attribute, I have got only two branches, yes and no. And then if I go from the body temperature, if I go to the cold branch, cold path, I have another node which is non-memel. So this is the internal node. If it's internal node, it is again broken into another subnodes. And finally, all the squares we are reaching, these are the Lisp nodes where they will represent the examples which belongs to memel and non-memel. So although here we have so many class, we have converted this into just two class problem, memel and non-memel. So again, that depends upon your problem objective. So all of so many classes here, my interest is only to identify memel and non-memel. So that's what I have done. So we have got this three Lisp nodes. Okay. So what is important to know over here? We are doing recursive partitioning. What operation we are performing, what process we are performing, or what algorithm we are running to partition our example at the root node, same process we will repeat at any of the internal nodes. That's what known as recursive partitioning. And we will keep on doing this until a stopping criteria is met. Okay. We'll talk about stopping criteria also. Right now we are growing a tree fullest till we reach the Lisp nodes. Then homogeneity. Here that's my stopping criteria, that all the examples at Lisp node here belong to mammals. Here. So all of this mammals example, which are mammals. After I construct a tree, they will go here. And some of the non-mammals will go here, some of the non-mammals will go over here. So that we are looking at the homogeneity. Then this is a top-down greedy approach. So it's a kind of a greedy algorithm. Top-down, that means we are starting from a top and then we are constructing tree top to down. And each split, because we are splitting at each node, is chosen to maximize the information gain or minimize the impurity. I'll talk about this. We'll talk this, but this is what the measure which is used. Now the question comes, how do we are choosing this body temperature over here? How do we are chosen gives birth as my left internal node? So that is because of this criteria, either minimize impurity or maximize the information gain. So we'll talk about it. This is only an example. I'm explaining an example of a tree and understand the tree. Say another data set over here. ID is first feature, homeowner second feature, marital status is third feature, annual income is fourth feature, and defaulted borrower is our class variable, class column. This is my training data, and then using a training data, I have used the decision tree construction algorithm, and I'm coming up with this decision tree. So say, because of the algorithm I have chosen, I got a homeowner as the root node. How many values I have in my homeowner? Yes and no. It's a binary attribute, so I'll have only two branches, yes and no. And if I go towards the yes path, I'm reaching to my Lisp node. If I go towards the no path, I have to construct another subtree. So say, for example, now I have chosen marital status as the feature for this node, and it is not a binary attribute, single, married, and divorced. But I'm still drawing a binary tree. So what will I do? Single, divorced will combine together and married will be separate. So this will be married or single and divorced. So our multi-class problem, we have not multi-class problem, our multi value attribute, we are converted into two values attribute. That's not always the case. I'll see multi-way split example I'll give, but this is a binary split example. And then in the married branch, we have reached to the Lisp node, but in the single divorced branch, again we have to construct another subtree. So we have chosen, say, income. Income is a continuous valued attribute. We have to discretize this attribute. That means again we'll use a different discretization techniques to find out a best split. Say for example, we have got a split of 80,000. So we will again divide into two branches, less than 80,000 or the greater than 80,000. And then we are reaching to the left nodes. This is how you will interpret this decision tree. So here we have got an example where I have more than two values. It's not a binary attribute. Here I have an example. It's a continuous attribute. And how we are constructing decision tree. This is one of the way of constructing decision tree where we are using binary splits. That means each of my node is splitted into two branches only. So even if you have more than two values in your attribute, or you have a continuous attribute, you have to convert it into the two values only. That's your binary splits. Then I'll talk about multi-way split. But this is a tree where my root node is homeowner. I can come up, there could be another tree where my root node is marital status. Then I'll get another tree. So based on the data set, always there could be more than one tree that can actually fit the same data. There is always a possibility. Okay, so now there are many algorithms which will help to construct a decision tree. Hunt's algorithm, CART, ID3, C4.5. This is what is mostly, or all of our current libraries are using this algorithm. There's a slight variation in algorithms. So this is a comparison table I have added. You will understand this comparison table only after we complete the entire theory of decision tree. So you can come back and then you see this comparison table. But I'll start the Hunt's algorithm, the first algorithm, very simple algorithm.
Ma'am, can we ask a question from, sorry to interrupt. Ma'am, can we ask a question from the previous slides, ma'am?
Yeah, tell me.
Yeah, not this one, ma'am, previous to this one.
Where?
No, previous to this one where we were starting. No. In the same problem statement where we're starting from home. Can we please go to the next one, ma'am?
Yeah, this one.
Yes, ma'am, this one, yeah. So, ma'am, how we are saying that in this slide, how we are saying that the marital status will be coming under the homeowner. We are saying that homeowner will be no, in that is a marital status. Like how we are relating the marital status with homeowner when the value is
wait. No. This is what I'm telling you. There is this, why homeowner is here, why marital status here, why income is here. All of this node placement we are doing, that's as per the algorithm. That's what I'll explain now. This is just assume this is one decision tree we have constructed. We can have another decision tree constructed like this, but there are the algorithm for this. That's what I'll explain. I'm explaining that now.
Okay, but there is as of now, like we have not identified the relation between these two independent variable x1, x2. Those relations in the table, right, ma'am?
No.
Okay, ma'am.
It's just an example of a decision tree.
Fine, ma'am. Thank you, ma'am.
One more question on the same slide. So if it is a homeowner and if he is a defaulter, then how do we give the decision tree? If there are some here all homeowners are not defaulters. Out of, if there are some 80,000 values, and if there are some owners and still a default borrowers.
1 minute.
Can it happen like that?
Okay. So okay. At the end, I have an example. How do we do inference? Okay. Let me just complete that. Then we'll come back.
Okay.
I was just searching where that slide went. Yeah, it's after this, where we perform the inferencing, right? Yeah. See, even that, what your question, what I'm trying to understand, that will be clear when we will see the entire tree construction algorithm. We have a one numerical, end-to-end numerical. I think what I've understood question, you will be able to. Then you will not have this question.
Okay, ma'am. Yeah.
Okay, so this is Hunt's algorithm, very simple. This is a general theoretical explanation mention. For every node, this is what we will do. Set of trending records that are associated with every node. So that every node of my decision tree will have some set of records. And these are the three conditions that we will check at every node. Let's start directly with the example. Yeah, our data set, I have these features 3, 4, and then I have what? Our class variable, and there are 10 examples, 1 to 10 examples. So what initial says, if our node contains records that belong to more than one class, use an attribute test to split the data into smaller subsets. So initially, how do we start? Initially, all our training examples belong to our root node, and the default class is no. So this is what you have to, from your domain expertise, you have to identify what is a default class. That this is one example of what? Defaulted borrower, whether person will default a loan or not. So from my domain knowledge, I want to set this default as no. So this is my root node. I have the class for this root node, default class is no. And all my training example, 10 training example belong to this root node. Okay, so you can say I've only just constructed a random root node. Then I'm looking at it and say this is my, see, the square is, that means always this is a leaf node. We start a root node assuming it is a leaf node. Okay. And I have got all the examples to my this leaf node. We can see how many examples are belong to no class. So you can divide and you can find out and how many belongs to yes class. We are seeing this. There are 7 examples belonging to no class and 3 examples belonging to yes class. So by this statement, this node contains records that belong to more than one class. Yes, I have a representation for both the classes. Then use the attribute test to split the data into smaller subsets. So what we will do, identify the attribute. How we will identify the attribute, that I'll discuss later. Suppose we have identified the attribute homeowner. It could be any other attribute, but see, we have identified homeowner. Initial default class, initial leaf class. Now we are growing a tree, so that becomes my root node. Initially my root node, because it's a initialization, root node is always a leaf node. Then in my first iteration, I'm identifying my homeowner feature as a root node, and it has got homeowner 2 branches, no and yes. Homeowner has got 2 branches, yes and no. And assume both the branches are reaching to my leaf node. And defaulted is no, defaulted is no. Because for every, it's a recursive algorithm. So when I start from a root node, it is always default as no. Now identify in both the leaf node, is this a correct leaf node, or I can further grow the tree from there. Now you can see on my yes branch, I have 3 examples belonging to yes class and 0 example belonging to no class. All of the examples are homogeneous. That means my homogeneity is achieved. There is no other way I can split it. You can see all of this, all of this belong to no class. And 0 belong to the yes class. 3 example belong to no class. So in the left branch, I have reached to the leaf node. But in the right branch, is this a leaf node, or I need to grow the tree recursively from this node onwards? You can see I have a mixed class representation. 4 belong to no class and 3 belong to yes class. So I can draw the tree. It's a recursive algorithm. So you have to identify which feature I can use it here to make a decision. Suppose, so this is my first iteration. So second iteration, now third iteration. We know this, I can grow my tree from the right branch. So pick up this, the next best feature, marital status. And marital status, I'm still doing a binary split. So we will combine single, divorced in one and married in as another branch. And then again, I'll have a leaf nodes and check whether can I grow a tree from the leaf node. On the left hand side, I have 1 belong to the no class and 3 example belong to the yes class. That means this is a non-homogeneous node. I can draw a tree further. I can grow a tree further from this branch. But on the merit branch, you can see all of my example are homogeneous. They all belong to the no class. So we have reached to the leaf node on the right hand side. This is the first iteration. This is the second one I did. I completed. A third I completed. In the third, I decided our algorithm can find out, okay, the single divorce branch can be further expanded. So from marital status is a single divorce branch. It's a recursive algorithm. So we'll repeat the same thing. Pick up the next best attribute, which is annual income. Annual income is my continuous attribute. So I'm dividing into a threshold. I'm finding out the optimal threshold. Less than 80K, greater than or equal to 80K. Again, left and right branch. And now these are the leaf nodes, and you can see these are the homogeneous nodes. This is only one class. Both of the leaf node has got only one class presentation. That means I have grown the complete tree, a fully grown tree. I have drawn. This is the training. So during the decision tree training, we are constructing a tree based on our training data set. Now, what is remaining, that how are we selecting all of this internal nodes? Okay, before that, this is the training done. How do we do the inferencing? Okay, so this is a final tree which will look like this. Homeowner, left branch, right branch. Left branch, we have reached to the leaf node. Which are the example which is going in the left node? Left branch here. Homeowner, yes branch, defaulted, no. I have 3 examples. So example number 1, 4, and 7. That has gone over here. Then here, each of the leaf node you can verify. Here example 2, 6, and 9 are going. 2, 6, and 9. So you can see all of them belong to the no class. So default is now you can take a majority class, which is no. Our algorithm, we started with a default as no. Then at the end, your default will be majority class. So this is no. Here also no, and only here where I have example 5, 8, and 10. They are going associated with this leaf node. 5, which is yes class, 8, which is also yes class, 10, which is also yes class. So I've got 3 examples for yes class. Majority is yes. So default class is yes. You can see while we are constructing a decision tree, we are actually partitioning our data set at each node. We have started with the root node where we have partitioned data set into first 3 examples, and 7 examples went down on the right hand side. Then again we partition here. This is what I guess 4, and this is 3. Then again at annual income we partition our data set further, 1 and 3. So this is another thing. Our decision tree partitions our training examples at each node. It's a recursive partitioning. Now, how do we perform the inference? Once we have grown the decision tree, we have to use this for a prediction. So say this is our unseen data, where homeowner is no. Marital status is married, annual income is 80K, and I want to identify what is the class, whether yes or no. I'll start with the homeowner and then no. So I have to go to this right branch, no. Then marital status is married. Then again, I'll go to the right branch, married. And I am reaching to the leaf node, no. So I will see homeowner is equal to no. Marital status is equal to married, irrespective of the annual income. Percent will not default. So that's why sometimes you will see there is a question mark here. As you can see, we are not checking. If you're going at this branch, we are only checking 2 feature values. We are not checking anything else. So if I write in this way, I can write no, homeowner no, marital status married. And if this is the branch I'm following, irrespective of the annual income, the class is going to be no. You can see these are simple if then else rules. So decision tree is nothing but if then else rules. If homeowner is no, if marital status is married, then my class is going to be no. It's if then else. Okay, this is just a graphic. How do we travel to the decision tree? Okay, now if you have got any doubt till now, you can ask me. Now I'll talk about how we are choosing this homeowner, marital status or income. That's what that theory will come. Yes. Can I go ahead? Let me see.
Ma'am, I have a question on this. From exam standpoint of view, do we need to draw all these trees and graphs, although those are lengthy?
Something that will come, something decision tree. Yes, it's a standard one question will come.
Thank you.
Yeah. Decision tree is not so that question will come. You would want decision tree to come in the exam actually.
Yeah, sure.
Okay. So how should the training records be split? So first we have to identify the attributes, and how should our splitting criteria, when should it split? Okay, let's see first. What till now I had explained binary split. So marital status, married, single and divorced. We had 3 distinct values in my feature, married, single, divorced, but we converted into 2 value. Either I can have single, married, divorced in one category, single, married, and depending upon your domain knowledge, you can combine values. Or we can have this multi-way split. Then it will not become a binary tree. We can have a multi-way tree. Multi-way decision tree is also possible. So in multi-way tree, if you have many partitions, okay, you have many values. As per the values, you can have individual branch going. Now, when we have a nominal attributes, like marital status is a nominal attribute. Single, divorced, married. So nominal data type. The order will not matter when we do a binary split. Whether we combine married with single, divorced, any of these things will not have an effect in the algorithm. It entirely based on your domain knowledge. But if we have the ordinal attributes like small, medium, large, extra large, so we can have this 4 different, there are 4 values. I can have 4 multi-way splits, or if I want to have a binary tree, I can combine 2 values. But which values can be combined? The order should be preserved. So you can see small, medium, large, extra large is okay because the order is preserved. Small in one branch and rest 3 in other branch is okay. But small and large in one branch and the medium and extra large in another branch, this is not okay. In this split, like short size, this split, our order is not preserved. I can also have something like small, medium, large. All of the examples belonging to this 3 class will be in one branch, and my another branch could be only extra large. This is also okay. But so for ordinal attributes, you have to be careful with the orders. And then if we have a continuous attribute, take a binary split or a multi-way split. But every time you have to identify the correct threshold. So we have 10K to 25K, 25 to 50K. Likewise, I can give the threshold and I can create a multi-way split. So we can perform a discretization. There are, I think we have discussed about discretization algorithm, histogram based or frequency based, count based. There are many more discretization algorithm. We'll do that pre-processing. We'll convert our continuous valued attribute into discrete attributes, depending upon how many different buckets you want to create. Or if I just want to create 2 bucket binary split, then I have to come up with the best threshold. So we can consider all the possible splits. How? again, that will come in the future slides. All of the possible values of your income in your data set can be a potential split. 10,000 can be a potential split, 25,000, 50,000, 80,000, any income could be a potential split. You can consider all possible splits, find the best one, and then come up with. But that could be a compute intensive. Or use your domain knowledge and find out which could be the best split.
I'm here in this split, like, can you go back to, 10,000, 25,000, like bracket is different. Like one side it is closed and open. So if in case 25,000 is the annual income, it should go in the first criteria, correct?
This is included, excluded, right?
Yes.
This is excluded. Then it will be included here.
Okay. Yeah.
Ma'am, should this node be always sorted from left to right?
Yes. If you the order, because this then it become a ordered ordinal attribute, right? More of ordinal attribute. So after discretization, you have to say you are converting into ordinal attribute. Then it will be, yes, you have to have the order.
So, ma'am, this is regarding the split on features, right? So first, but before that, we have like 8, 9 features, right? So which features is first we need to take is important, like.
That's I've not discussed yet. That's what I keep on telling. That's
Okay.
still remaining.
So you are going to take, okay.
Yes. Okay. See, it's 10:30. It is okay. 15, 20 minutes if I take now today and explain, because once I start that, that will take at least 20, 25 minutes.
Yeah, I think it's okay.
Yeah,
No
this
problem.
is theory.
Please take.
There's a theory of all of this, Gini and entropy, and everything will come. So it's good for you. We will solve this one numerical, then I will end it. So you'll have some time to go through it. Okay. But it will take some time. I cannot stop in between once I'll start. Okay, fine. So I'm going back and I'm just trying to show you something here. Okay, here, in this example, if you look at all the Lisp node, what do you observe? What is a common thing in all of these Lisp nodes?
Defaulted no.
0 in the second variable.
Zero.
All of the Lisp node, all of the example belong to same class, either yes or either no, right?
Yes.
So all of these are the pure nodes. So comes a concept of purity. So this is also pure Lisp node. This is also pure node, and all of this are pure nodes. Okay, suppose I have this three. So first I'm just explaining the concept of purity. We have a gender. I have yes and no, 2 branches. In yes branch, I have 6 examples belonging to 0 class, class C0 or 0. For example, to the 1 class. No branch also similar, like 4 and 6 combination. Then I have another feature car type, which I'm doing multi-way split, and I get this distribution, class distribution. So you can say class 1, class 0 is 1 example, class 1 is 3 example, this is 8 and 0, this is 1 and 7. Compared to customer ID, if I take that as my splitting attribute, all of these examples are, you can see, all of my Lisp nodes, they have 1 class representation. Now, with this, like 3 of this, which one is a purer node? I just explained what is pure.
The first one?
Gender or customer ID?
Customer ID.
This is the purer node, because what we are getting, all of my Lisp nodes have got only 1 class representation. What about car type?
Multi-representation.
But still it is pure, because the imbalance is high. We have more examples belonging to the same class. So it is a comparative analysis, and compared to the gender, where we have almost 50% representation for both the classes. So it's an impure class. So this is a comparative analysis. I want purer class. So that question will always come. Okay, if I want a purer class, I should always choose customer ID as the splitting criteria for any time. But hold on to that. We will not, in practice, we should not use a customer ID. That we'll discuss in the next class. But out of gender and car type, a good node split is a car type because it is more purer compared to gender. So here we'll have the comparison, and which one is more purer will be taken as the car type. So here the question comes, how do we measure the purity? This is the end result. We are able to see the purity by looking at this numbers, class representation. Okay, we can measure the purity, but how do we find the purity? How do we, find this split? So here the concept of comes, the node impurity comes. Say I have this leaf node. Due to one attribute, I'm getting this leaf node where I have both the class representation as 5, 5, and here I have one class dominates the other class. So both of this, which one is more purer? Obviously the last one, the second one, right one is a more purer. So I will relate this concept of impurity with a probability or the information theory. High degree of impurity is high uncertainty. Why I call this as a high uncertainty here? Suppose I am here. Okay, we have some decision. Yes and no. See, maybe gender, female and male, and we have 5 example, and here we have a 5 example. Now, if you want to make a decision, you would want to travel the tree at this node. Sorry, this is a wrong representation. At any node, I have 5 example belonging to the yes class and 5 example belonging to the no class. And if I want to make a decision, whether the default is yes or default is no, it's very difficult to make a decision because both have the equal representation. Even if I have this way, 6 and 4, it's very difficult to make a decision. It could be yes class, it could be no class. So when we make a decision, it is high uncertainty. When we relate a high uncertainty to the information theory, say when there is a high uncertainty, we have a low information content. It rained heavily in Shillong yesterday. The probability of raining in Shillong is always high. So the information content is very low compared to when I say that there was a heavy rainfall in Rajasthan. Probability of a heavy rainfall in Rajasthan is very low. When a probability is low, the information content is high. So first I'm relating information with a probability. I'm quantifying information using a probability theory. And I'm also relating high impurity. So low degree of impurity, that means there is a high information content. So impurity, information theory, and the probability theory, they are linked together over here. First of all, information, we are quantifying the information, high information, low information using a probability theory. Information is inversely proportional to the probability. So this proportionate sign, we want to generate a mathematical expression. So we'll take a log. So information is log of inverse of probability. This also can be written minus log 1 by probability. That's my information. So based on this information theory, we'll have 2 measures which will measure the node impurity, Gini index and entropy. This is a formula for the Gini index, and this is a formula for the entropy. So as you can see, entropy there's a minus sign over here. First, I'll concentrate on the entropy. If you understand entropy, you will understand easily Gini index. It's a probability multiplied by log of probability. So as the uncertainty increases, our entropy also increases. Entropy is a measure of purity. So if entropy increases, that means impurity also increases. Now go back to our decision tree. Why we are studying all these things? We need to find a measure which will help us, like for what? Which variable, like which feature we should split the data that lead to the underlying child nodes being the most purer or most homogeneous. Like in this 2 example, this is more purer than this. So I want to choose an attribute. I want to choose an attribute by splitting examples on that attribute. I will get this purer node. So that's what is the definition of. In other words, I can say splitting on attribute, that is splitting on a feature, should reduce the impurity, should reduce the entropy value. Okay, now some simple mathematical numerical. Say I have got class. No, let me complete. I'll only answer after that. Let me complete. This is not just something which 1 or 2 slide. It is the entire set of slides, and then I'll answer your questions. Class 0 and class 1. Say this is my representation of a node, leaf node. Class 0, I have a 0 count. Class 1, I have a 6 count. Okay, so by just looking at this count, what you can see, is it a purer node or impure node?
Purer.
It's a pure node because all of my examples belong to the same class. And just let's calculate the values of Gini and entropy. I have just 2 class. I need to calculate the probability. Probability for a 0 class is 0 by 6. Total examples are 6. Out of 6 examples, 0 belong to the 0 class. So it's 0 by 6, 0. And out of 6 examples, all of them belong to the another class. So probability is 1. Use this probabilities, apply the Gini formula. You will get Gini of 0 and the entropy. Same thing, apply the entropy formula. You will get entropy of 0. So this P of IT is actually a probability value, a proportion value. And we are calculating with a log to the base 2. So for the purer node, we will always get a Gini value of 0 or entropy value of 0. Compared to look at the last number, 3. So what will I call this as? Impure node. The example belong to this leaf node. 3 belongs to class 0, 3 belongs to class 1. High uncertainty, whether I should consider as a class 0 or a class 1. Both are 50% probability when I want to predict the label. So when we calculate Gini and entropy for that, use the formula and then calculate it. Gini will be 0.5 and entropy will be 1. That means whenever we have equal representation, entropy is 1. Higher the entropy, more purity. Higher the Gini value, it is more impure node. So Gini value will go between 0 to 0.5, its range. And the entropy will go between value 0 to 1. And we have something in between, some count. And then we calculate value of Gini is this coming out to be, entropy is coming out to be this. This is just a mathematical calculation, how to calculate Gini and entropy and what is its interpretation. Okay. Yeah, tell me, somebody wanted to ask anything? Yes.
Now, what is the submission here? Like, do we need to calculate the Gini values all we calculated from the formula?
No, sorry, what are you asking?
Here, like Gini index is equal to 1 minus summation of the probability, now the last square formula in the square box. So what does this mean? Like, do we need to calculate the PT for each of these
class
kind of
values?
examples?
Class values. So we have 2 classes, right? Here 0 and 1. We have just 2 classes. So we are doing it for each of the classes. C is the class, or I can say unique values or the class, unique values in the class. So we have yes and no like that here. We'll see one end-to-end example. It will be more clear.
Okay, fine.
Okay. Now, when we draw a decision tree, there are many child nodes. Like for multi-weight split, there are 3 child nodes. For a binary split, there are two child nodes. Like we can have multiple child nodes. So there's something called a collective impurity of a child nodes. So this is a collective impurity when we use a Gini formula, and we use a collective entropy of a child nodes when we use the entropy formula. For each of the child nodes, we will calculate the entropy, and then we will sum of them together, sum all the values together, and first we multiply by this ratio, number of examples of that child node, and number of examples at the parent node. So this is a formula. So based on this, we'll come up with some another measure called information gain, which is the parent impurity minus the child impurity. Okay, a lot of theories mentioned. Let me first take an example, then I guess this theory will make any sense. Okay, I'll come back to this theory once I'll take this into an example. Okay, so I have this features x1, x2, x3, x4, x5, and I have a variable y, day, outlook, temperature, humidity, and wind. So these are the my feature values. It has got certain values, and all of them are discrete values, no continuous values. Play tennis has got just two values, yes and no. It's a binary class problem. Okay, so what we will do, this is my information gain formula. First, we will create the entropy of the parent. That means entropy of my class variable. And then we'll subtract it and calculate, we will sum and calculate entropy of each child. So how do we solve this? How do I solve this? First, I will calculate the entropy for the class variable, which is play tennis. How many example we have, positive, and how many negative? No class 1, 2, 3, 4, 5. So we have 5 negative, and rest of them are
9
positive. So S, that's my entire data set. We have 9 positive examples and 5 negative examples out of 14 examples. So we'll use these numbers to calculate this entropy. For each class, now I have just 2 class, positive, negative. So I can write my formula like this. Probability for a positive class into log of probability to the positive class minus probability for the negative class into log of probability to the negative class. So I simply show you for a positive class probability. Can you tell me what is a positive class probability? But just by looking at these numbers.
5 by 14.
9 by
Positive
14.
class 9 by 14.
9 by 14.
And for negative class, it is what? It is 5 by 14. And then simply arrange in this minus 9 by 14 into log of to the base 2 9 by 14 minus what we have 5 by 14 and to the log base 2 5 by 14. Calculate this. We are getting entropy of our parent is 0.94. Where now you can relate with your decision tree. You have a default class, root node at the beginning. Everything else, all the examples are at the root node, which is a leaf node. And for that leaf node, entropy is very high. That means it's a very impure node. You can clearly see over here, I have 9 positive examples, 5 negative examples. It's an impure node. So I need to split that node. So we'll come. How do we split? We have to take all the features individually and calculate the information gain. So first thing, what we will do, we will consider a wind attribute. So the entire calculation for the wind is shown. This is a wind attribute, and we will find out the information gain between the parent node, which is the entire data set, and the wind. So now for the wind class, I have how many, wind attribute. I have how many unique values, weak and strong. Only I have 2 unique values. I will calculate this information separately for the weak and strong class. That's class representation. So for a weak class, how many weak class I have? Oh, let's see strong. That's easy. Strong 1, 2, 3, 4, 5, and 6. So out of 6 strongs, total as 6, 3 belong to no class, and rest 3 belong to yes class. So 3 positive example, 3 negative example, and total examples are 6. So where wind value is a strong, and then for that we are looking at the class distribution. Then we will look at the weak value. When the wind value is weak, we got 6 positive examples and 2 negative example, total of 8 example where attribute value wind is weak. So once we have got this, the next is to calculate the entropy for the strong value of the wing and then entropy for the weak value of the wing. It's a recursive algorithm. We'll repeat the same thing. It's the same recursive formula. So initially we consider the entire data set and we use this class information. Now I'm choosing an attribute because I want to make a split at that attribute. So I'll calculate the child entropy. What will be the child entropy if I will split my root node using the wind attribute? So I will calculate entropy for the strong class. S equal to strong when the wind equal to strong. Now while looking at it, what can you say? Do you really need to calculate the entropy over here? What will be the value of entropy? Okay. I've shown this example here. Yeah. When both the class representations are equal, what is the entropy coming out to be? 1. So that always happen. You can save your calculation time. Whenever you observe, when both the class representations have the equal representations, so entropy is 1. Okay, now we have to calculate for the weak wind attribute value 6 plus 2. So same thing, find out the probability. So for a positive class, probability is what? 6 by 8. For a negative class, probability is what? 2 by 8. So we have done minus 6 by 8 into log of 2 6 by 8 minus 2 by 8 log of 2 by 8. So entropy for the weak attribute value, all those examples are 0.811. And then I'll use the information gain formula, which is the entropy of my parent. And if I choose a wind for a splitting criteria, what is this? So out of 14 example, which belong to the weak class? So you find out weak class. 8 example belong to the weak class and 6 example belong to the strong, sorry, not weak class. 8 examples belong to the weak attribute value and 6 example belong to the strong attribute value. So in my information gain formula, this Sy by S is what? S is the total number of examples. NSV is a unique value. For each of the unique value of wind, how many are there? So for a weak unique value, I have 8 examples. For a strong unique value, I have 6 examples out of total 14 examples. Multiplied by their individual entropies that we calculated. So it's 0.811 and 1.0. And then final information gain is coming out to be 0.048. So now what is where does this value fit in? Okay. Initial, I was having a leaf node where I had, if you remember, I always start with the leaf node as my root node, where we have the example, total 14 examples over here. And I can see this 9 example belong to positive class and 5 example belong to negative class. It's impure node with the corresponding entropy value that we calculated is 0.940. So we can split this. I want to decide how do I split it. That was a decision you all had in mind. Why should I choose this feature as a splitting? I showed the calculation of wind. Wind has got 2 branches, weak and strong. It's a binary value. And when we split, if we split with the wind, 8 example are going on the weak branch, 6 example are going on the strong branch. So after we split, what is a reduction in entropy that we observe on both the branches? So this is what We observe one branch, it is entropy is reduced. The other branch entropy is increased. This 1 and 0.811 we got from here. These are the values we calculated. So what I'm explaining now is the interpretation of those values. Okay, and then based on these three entropy values, we use the gain formula and calculated the gain, which is coming out to be 0.048. Now suppose you have to try, after wind we will try the humidity. That's another feature, another attribute in my data set. So we picked up this humidity. It has got two values, high and normal. Yeah, so humidity is this, high and normal. I just have two values. It is high and normal. And the calculations are not shown, but you can verify and you can calculate. My 7 examples are going on high side. And again, the 7 examples are going in normal side. But you can see, is there any reduction in entropy? These are the two values of entropy coming. In one branch, there is an increase in entropy. Another branch, there is a decrease in entropy. We want both the branches or all the branches, entropy should decrease. So if we calculate your gain value, this is a gain that we will get. Similarly, we have 4 features. This one, the calculation is shown. We have got a gain when we are splitting the entire data set using a wind attribute at 0.048, with outlook 0.246, and for humidity some value, with temperature another value. Out of this, you have to pick up a maximum gain. So you can see 0.247 is a maximum gain. So we are getting this gain by splitting the entire data set using the outlook as an attribute. So what we have achieved on this data set, we have now achieved what will go in the root node. The outlook will go in the root node, which has got 3 values, sunny, overcast, and rain. There are few examples, like 5 example going to the sunny branch, then again 5 example going to the rain branch, and 4 example going to the overcast branch. Overcast branch we have reached to the purer node. So it's a leaf node. But with the sunny and the rain branch, we have got the impure node. So I can grow the decision tree from the sunny and the rain, both branches. It's a recursive algorithm. So what we did to identify the outlook over here, will repeat the same thing on both the branches separately. So again, that one branch is shown over here as the calculation. Let's take the outlook equal to sunny branch. So this is outlook is equal to sunny branch. I'm taking this. Here I have to make a decision which attribute I should pick up for splitting. So I have a choice. Should I pick up humidity, wind, temperature, outlook? We have to repeat all the algorithm again. So let's test it for the wind again. So when outlook equal to sunny branch. So let's just look at the sunny branch examples. 1, 2, 3, 4, 5. Now my question is over here. What will become S? In the root node, I am putting everything, all my example at the root node. But now I'm looking at the outlook equal to sunny branch. So that my leaf node, how many examples are going? We just saw here. Only 5 examples are going here. So those 5 examples only we have to consider this in calculation. That will become our parent node. So our parent node, this S is entropy of the parent node. Now we have just 5 example, and this is our parent node now, where outlook equal to sunny. I have 5 example. So when we calculate its entropy, same formula. So we'll have this what? Minus 2 by 5 into log of 2 by 5 minus 3 by 5 into log of 3 by 5. So that's where we have calculated entropy of a parent branch. Then children branch. Now what are the children here? We are taking a wind attribute. So if you look at it, sunny and weak combination, sunny and strong combination. So I've got sunny and weak. How many are there? Sunny and weak? Sunny and weak. We have 3 examples going to sunny and weak combination, and I have 2 examples going sunny and strong. Sunny and yes, strong, 2 example. Out of this 3 and 2 example, how many belonging to the positive class? 1 belong to the positive class, and how many belong to the negative class? So this is a positive class and the negative class. Once I get this numbers straight, I have to use the direct entropy, same entropy formula, because my parent node is now this, and this 2 are the child node. I've already calculated now parent node entropy 0.97. We have to calculate both the child node entropy. These 2 are the child nodes now. And this is the parent node for a sunny branch. Okay, so weak and sunny, so it is same 1 plus, so this is 3, this is 3 out of 3. So it's 1 by 3 and 2 by 3. Positive class 1 by 3, negative class 2 by 3. Calculate. For sunny and strong, you don't need to calculate anything because both of them have got equal representation. So entropy is going to be 1. And then use the same formula. This is a parent. This is a child. This is another child. So parent entropy minus, we have got child entropy. We have got total of 5 examples for the parent. Out of 5, 3 belongs to sunny and weak, and 2 belongs to sunny and strong. So it is 3 by 5 and 2 by 5. S by V and S. And gain we are getting is 0.019. So what is this gain? I will write down. Gain when my parent node is outlook with a sunny value and attribute wind. Same thing we did for the other features, and out of this humidity provides the best information gain 0.970. So we can split that sunny branch using a humidity. So how will it look like? We have outlook sunny branch, and we are going to split this, and we are going to put the humidity here. So we have, okay, let me just. Yeah, so we calculated for sunny branch, I needed to grow the tree from the sunny branch, and this become my parent node with all 5 example in the sunny branch. We have identified humidity. So this branch is now further divided into, split into another subtree, again high and normal. Overcast, we don't need to grow the tree, but same thing for the rain branch also, you have to see which node to be chosen as a best split. And say suppose this is what we have found, wind is the best attribute that we have identified for the rain branch. So we are growing the tree, and then we have got this. At the end, we are able to divide our example correctly among all the branches. No, yes, yes, and no. We got homogeneous nodes, so we have reached to the leaf nodes. So now it is clear that how are we making these choices at every node, whether it's a root node or internal node, which attribute to be chosen. So what are we doing? If I go back here, we started with the entropy calculation. At every node, we need to choose where my information gain is higher. After splitting this 14 examples, like at the root node, I had 14 examples. After splitting that, I should gain the, I should get the higher information gain or lower the entropy. That means the node impurity should be reduced and the information gain should be increased. So if we look at the entropy value will be less and the information gain value will be high when you compare different attributes. Like here we have humidity and wind. Then we can compare here. their gain is higher. Okay, this was one end-to-end example. And then now if you will read this theory, I've added one extra slide to understand the relation between entropy and information gain. We'll discuss next time. There's a lot of theory, but now this theory will make sense if you have seen this end-to-end example. Do you have any doubts here?
Ma'am, I have two doubts. So when we are finding the next feature, like in the tree, right? So we cannot repeat, right? Let's say we have taken the outlook as a root node, and then we came to humidity, and
Yeah, understood. See, there is a different algorithm behaves in a different way. This algorithm, which is mentioned in Hunt's algorithm, okay, it's also given in Tom Mischel book. It says you should not, I mean, you should not take it. It's separate, the attribute which is already taken. But the sklearn decision tree, what is implemented, it considers all the attributes again.
okay.
So there's a slight variation with all of these algorithms.
Okay. Okay. My second query is that so the outcome of this research basically is that we get the leaf nodes, which is the pure leaf. I mean, which is the output
Purer.
purer. So what if I get equal values like 5 class 1 and 5 class 0? So which one to
There's
take?
a possibility. Yeah, that we'll discuss in the next time. That's possible. Yeah. Then if 5, then you have to randomly take anything.
Okay.
Lot of those details we'll discuss, but here I'm just explain in this class how to grow the complete decision tree, right? From impurity measure also calculate. Do you have doubt in this?
No, it's clear. It's clear.
It's clear. Okay. So please take some time, read the theory, and this is very simple example.
Ma'am, I just have a little doubt on the last part. Like
Those who want to leave can leave. The class is ended. Manoj Chaurasia said is always your choice. Okay. Please stop writing like this kind of comments. I asked you whether should I, extend or not. It's totally up to you. You can leave the class. Yeah. Please,
ma'am,
please.
I was saying
Class is ended.
was
Those who want to leave can leave.
in the last part, ma'am, you're saying that the gain. So just a little confusion. So when the gain is increasing, we have to. That is a good choice to have, right?
Yes.
So we calculated individual entropies for the leaf nodes, and we then calculated the gain by
Correct.
using the entropy of the parent node and the child nodes. And we saw that the gain is increasing. So gain is increasing means the child nodes will have the lower entropy.
Correct. Lower impurity, lower entropy.
Okay.
Yes, you are correct. You correctly understood. Yeah. Anything else? Anybody else?
That's the reason, ma'am. Like when you were explaining that rain in the Shillong example, like that is not very informative, basically, correct? Because information gain is very less.
Information is gain, not information gain. Okay. Information content is less.
Yes, information content
Gain,
is less.
see, then we are quantifying that, okay, in terms of entropy, then information gain. That's way of quantifying. So information gain is related to split. How much gain you are getting in terms of information that way. So information gain is different than information.
Okay.
Yeah. Anybody else?
Ma'am, just one more question regarding the TPR and FPR part.
Okay. Let
Ma'am,
me
I
see
understand.
this.
I understand the definitions individually, like how we are trying to get an idea of how much true positives we are getting and how much false positives we are getting. But is there any like intuitive relation between these parameters? Like like if the TPR will be high, then FPR, like should we ponder upon such things? Like will they come handy in exam or anything? Like
No,
any
exam
relationship?
perspective, don't go into that detail. But yeah, it is good to note their true positive rate. So you try to understand their formula, then you will be able to understand what is the relation. Intuitive understanding. Yeah. So
Right,
first
like
try to
if
understand that formula, right? TPR, FPR.
Yeah, I understand them individually. Like TPR would be
Ah.
like in the positives. Do I see any false positives as well? For the precision, the definition would be like, if we are seeing the true positives, then am I seeing any false positive as well? The precision will tell me that, and TPR will tell me like among all the actual positives, how much positives am I really getting?
Able to
So
catch.
yeah, able to catch. So, but if I am getting one parameter, do I get the idea of another parameter? So do I need any intuitive understanding in that? So that's what I'm asking.
I don't think so. I'm not actually able to connect your question, but I don't think so. Maybe some case study specific if you have. That way might be. So you want to find a relation between TPR and FPR, whether one is increasing, other is decreasing or increasing, something like that?
Yeah, is there any relation between them?
No. Okay. Like F1 score and no, I don't think so.
Okay. Okay.
Ma'am, I have a
Huh.
query.
Huh.
So I am growing my tree. I mean, this is a decision tree. Growing my tree, I came to a branch where both my nodes are having entropy as 1. So, I mean, it's a binary node basically. So I have entropies as 1. So we can't identify the features further.
Randomly, you have to pick up randomly. Very peculiar cases are like that, right? When you will get this kind of situation.
Okay.
Yeah, randomly you have to pick in this case. Okay, anybody else? I'll stop the recording now.